Hello, and welcome to another edition of Physics Online, in which today we'll be talking about some very important equations. These are called the kinematic equations, or basically the equations of motion. They're so important that I want you to memorize them because we will be using them throughout the rest of the year. One of them you already know. This one is that the velocity, the average velocity, can be found by the change in position, which we call the displacement, over the time period in which that change in position takes place. And more often we're going to write it more simply as x over t. Now you can come up with an equation for the displacement by simply solving this equation for x. So I want you to write that answer right in here. In addition, I want you to write an answer to this question. Suppose you observe a car moving with an initial velocity, v sub I, of 20 meters per second, and 1 second later it has a velocity v sub 1 of 25 meters per second, and then another second passes and it has a final velocity of v sub f equals 30 meters per second. What I would like you to do is see if you can calculate the average velocity of the car during this 2-second time interval. So push that pause button and see if you can answer both of these questions. Use a pencil so you can erase, and we'll come back and check our answers. Let's see what we have for answers. First of all, we can come up with an equation for displacement by simply multiplying the average velocity times the time in which it's traveling at that average velocity. Now, in problem number 2, we asked to find the average speed during a 2-second time interval. We were told that the initial velocity was 20 meters per second. 1 second later, the new velocity was 25 meters per second. That's the average. 1 second after that, the final velocity is 30 meters per second. In other words, this is the average velocity because it's halfway between 20 and 30. And indeed, it turns out that for objects undergoing constant acceleration, the average velocity can be found by this important equation right here. The average velocity is the sum of the initial plus final velocities divided by 2. In other words, it's simply an arithmetic average. This is only true for situations involving constant acceleration. And indeed, that's what we had in this situation. The acceleration was 5 meters per second per second. We can see that because this says how the velocity changes. Every second that passes, the velocity increases by 5 meters per second. So in other words, the initial velocity was 20. 1 second later, it moved up to 25. 1 second after that, up to 30. So we can see we are undergoing constant acceleration. And so in this time interval, the average velocity was indeed 25 meters per second. Now, let's take a look at another kinematic equation. And this can be derived from something we're already familiar with, and that is the equation for acceleration. Acceleration is indeed the change in velocity per unit time. And we can write this change in velocity as v final minus v initial over the time period t. Now I'd like you to solve this equation for the final velocity. So hit that pause button and fill in this blank right here. Let's check our answers. First of all, we can multiply both sides by t, and we get a times t equals v final minus v initial. Or, solving this equation for v final, we add v sub I to both sides. So we get v sub final equals v initial plus acceleration times time. So this is another very important kinematic equation, and you should commit this to memory. What it says basically is that our final velocity, v sub f, what does it depend upon? Well, it depends on the initial velocity that we have, and there's any added velocity that might occur if we're accelerating. Notice that if the acceleration were 0, imagine this term were to disappear, if a is 0, then the final velocity would be equal to the initial velocity. In other words, we would be going at a constant velocity. However, if we are indeed accelerating, we know that our velocity would change. How would it change? It would change by this added term right here, depending on the acceleration and depending on how much time it accelerates. Now we could check our units to make sure that we really do have velocity units on this side and velocity units on this side. Here's our units. Final velocity in MKS units is simply meters per second. The initial velocity is also meters per second. Acceleration is meters per second squared times time, which is seconds. But this second would cancel with this second, and therefore we're left with meters per second. In other words, we really are adding up two velocities. The first velocity being the final velocity that we end up with, equals the initial velocity that we start with in meters per second, and then the added velocity that may result from acceleration if we are indeed accelerating. Let's move on and derive another equation of motion. We're going to do it by going back to some graphical analysis. Let's examine this velocity versus time graph. We have velocity along this axis here, and we have time along my horizontal axis. We're going to make this very general. We're not going to use numbers. We're going to say that when we first observe this object, it has an initial velocity v sub I. And a little bit later on, it has a new velocity v sub f. And so as you can see, the velocity is changing. In fact, the velocity is increasing as time passes. In other words, this object is undergoing constant acceleration. What we want to do is to find the displacement that occurs during this change in velocity. And to do that, we're going to break this up into a rectangle and a triangle. That is, remember, to find displacement, we need to find the area between the curve and the time axis. So here's what we have. For the rectangle, we have the base as being a certain time interval, which we're going to call delta t. We have the height of my rectangle being the same as the initial velocity v sub I. In other words, it went from 0 to some initial velocity, so that's the height. We're just going to use these variables. In terms of the triangle, it has a base also equal to delta t from here to here, and it has a vertical height equal to v final minus v initial. That is v final minus v initial. That's this height right here. But we're simply going to express that as my change in velocity, which it is. Now what I would like you to do over here in this space, I want you to write down the total displacement, which is simply the area of my rectangle added to the area of my triangle. So use these variables and the equation for the area of a rectangle and that of a triangle, and fill in the space in here. So here's what we have. My displacement delta x, as before, is the sum of the area of my rectangle plus the area of my triangle. Now the area of my rectangle is simply vi times delta t. That is, it's vi, this height here, times delta t. And the area of my triangle is 1/2 the base times the height. The base is also delta t, and the height is delta v. But understand that this object is undergoing an acceleration, and acceleration is delta v over delta t. Solving this for delta v, multiply both sides by delta t, and I get a times delta t. Now I'm going to substitute this expression right up here for delta v. I'm going to substitute a delta t, and this is what I get down here. So now my equation for displacement is vi times delta t plus 1/2 a delta t squared. There's a delta t times a delta t gives me delta t squared. Now I don't have to write down the deltas. Okay, we're talking about a change in time, a time interval, and I want to keep things as simple as possible. So I'm going to simply write my equation for my displacement as equal to the initial velocity times the time plus 1/2 the acceleration times the time squared. So what I want you to do is check the units. Look at the units, MKS units on this side, and check to see if they make sense on this side. Ignore the 1/2 for the time being. We just want to check the units. So push that pause button and check your units. Checking our units. On this side of our displacement equation, MKS units would be simply meters. The initial velocity VI would be meters per second. The time is seconds. And as you can see, the seconds would cancel, and I get meters. Acceleration now is meters per second squared. The time is squared, that's seconds squared. So this second squared would cancel with this, and I'm left with meters. So indeed, meters on this side is the sum of meters here and meters here. And note that if the acceleration is 0, then our displacement only depends upon the initial velocity and the time. Also, if we're starting from rest, if our initial velocity is 0, this term disappears, and so our displacement would simply be equal to 1/2 a t squared. Here's an application of this equation. Suppose we have an object in free fall on the earth, such as a ball, like a tennis ball, that we simply release from rest. In other words, it has an initial velocity equal to 0. And we know that if it's in free fall, then the only force acting on it is the force of gravity. And therefore it's undergoing a constant acceleration, a, which is equal to positive g, where g stands for the acceleration due to gravity, which you know is around 9.8 or 10 meters per second squared. What I would like you to do is substitute this information into this equation up here and give me the expression for the displacement using these particular quantities, and then see if you can sketch a graph of this displacement equation versus time. Just a little sketch. Push that pause button and let's see what you can come up with. Okay, here's our answer. If we're substituting the initial velocity to be 0, then this term right here disappears. 0 times t is just 0. The only thing is left is 1/2 a t squared, but we said that this object is free fall, so the acceleration is indeed g, 9.8 meters per second squared, so we can substitute for a, the value g. So this is a very special case of that equation in which we're talking about an object that's released from rest and falling freely on the Earth's surface. And notice what kind of equation this is. This is a quadratic equation. There's a squared term here. And indeed, you know that the graph of a quadratic equation is a parabola. Indeed, this is the graph of the displacement of this falling object. It is parabolic. Well, actually, it's half a parabola. We don't see the other half over here simply because there's no negative time. So really, it's half of a parabola. And that is what it looks like in terms of the displacement for an object in free fall on the Earth. Now there's one more equation that we need to use and understand. This one's a little more complicated. It's basically the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. This is an important equation because there is no variable t in it. In other words, there is no time in that equation. And sometimes we will come across a problem in which we do not know the time. We don't have any information about the time. But for example, we may know the initial velocity of the object, we may know its acceleration and how far it travels, the displacement x, and we could calculate its final velocity. Or if we knew its final velocity and its initial velocity, and if we knew the acceleration, we could calculate how far it traveled during this change in velocity from v initial to v final. But we'll talk about this a little bit more, and we'll have some examples in class. So for now, I thank you for tuning in, and I hope you learned some physics.